Okay. Can you see the slide?
Yes.
Okay. Very good. So let me try to put, should I turn on chat, or how would you like me to do this so that
Just feel free to do that, what you think it is the best way to do.
I see. Okay. I'm trying to arrange these windows here properly so they're not in my way.
Yeah.
Just give me a moment, please.
Yes, sure.
There we go. Okay, almost there. So let me back this up one time here. Whoops. Here we go. Okay, so here's the starting slide. Let me just begin by saying that I'm delighted to be asked to be a part of this workshop, and and greetings from sunny Los Angeles, where today it's raining a lot, very strongly. There's a lot of rain out there. I realize this is a workshop on artificial intelligence, also relating to ubiquitous cities. My subject today is not directly related to ubiquitous cities, but only in the sense, that cities are created by humans, and cities are populated by humans, and part of artificial intelligence is about human thought and how the human brain works. And so my talk today is focusing on humans, how we can simulate humans, including their bodies and human brains that control the body. And so I'm going to take you on a trip, basically, of research that covers approximately 30 or so years in my group, from my group mainly. And that research has been centered on human simulation. So it's at the forefront, the cutting edge of human simulation these days. And I want to particularly get into how the brain works in conjunction with the simulation of the human body, also simulating the human brain and the neural networks in the brain, so that we can do neuromuscular control and ultimately sensory motor control, which includes perception, primarily through vision is what I'll be focusing on, but perception and action, so in a complete sensory motor loop. As Rita mentioned, I'm a professor at UCLA in computer science, and I direct the UCLA Computer Graphics and Vision Laboratory, where we combine graphics and vision. And on the graphics side is simulation, including physics simulation, but biomechanical simulation and biological simulation in general. That's where the biomimetic part of my talk comes in. So we're trying to be as accurate as possible to the biology of the human body and the brain, and try to simulate that, but also vision, which is an important part of my research over the years in computer vision and simulating the visual process in humans as well. So that's biomimetic vision. Okay, so should I talk for approximately an hour right now, by the way? Or how?
You can just talk for an hour. Of course, you can also do something that you like to do. So I'm not sure, some of them, they just demonstrate something. Like, for example, previously, Stan Fana, that he has tried to demonstrate his Google Glass. And then some of the display that he has done. Yeah, so you just like, feel free. I mean, feel free to do that. Do the things that you think that it is like
Well,
you think fit.
but according to the schedule, is it so? So I speak for an hour, then there's a break, and then speak for
Yeah, right,
another.
right. Of course, you can also do something as like teaching them how to like do some simulation for deep learning,
Yes, I'm gonna.
neuromuscular.
This this talk is a very visual talk. I have lots and lots of images and videos to show. I'm not going to delve too deeply into the mathematics because that that would be an entire course. In fact, I teach a course which is a unique course in the world. I think nobody else teaches a course like this really. So I teach this as a graduate course, and it involves artificial life in realistic artificial life, meaning realistic simulation of animals and humans, as realistic as possible. And so this is sort of at the tail end of that course is where I get into this material, and on human simulation after we've covered how to model and simulate plants, and then go into animals, starting from lower animals and progressing up to human human animals, and trying to model and simulate humans as accurately as possible. So, with that course, which is an entire quarter, I get into the mathematics of things, including the mathematics of biomechanics and all of that. But I can't get into that kind of level of detail in today's presentations. Okay, so the work that I'm going to show you also is relevant to robotics, because robotics researchers have, or at least one big component of robotics research has been devoted to anthropometric robotics, or modeling robots after humans, such as the one you see here, which is a fictional robot. It doesn't exist. This is actually a computer graphics image, in fact, that has a computer graphics human, photorealistic human female, plus the robot, which is not a physical robot. It's a kind of like a computer graphics robot. So, but this is sort of the future in some sense of what many people in robotics are dreaming about, that we'll have robots like this that are intelligent robots that look like humans and that will help us or maybe hurt us, perhaps. But this is sort of an idealized future. But in reality, the present looks more like this. What we have today, sort of at the cutting edge of robotics research, anthropometric robotics, or anthropomorphic robots, look more like this. I mean, they still have wheels. It's very few of them can actually walk or balance. Those that do are complex, just like these ones over here are very complex. They're usually not operating very well. They need adjustments and all of that. So mean time between failure is very high, and so they're not anywhere near as robust as the human body. And in fact, they don't really look like the human body in many instances. I mean, this is kind of state-of-the-art work over here, depicted in these images. And this is, you can see this project is multiple research institutes putting this together. But the fact of the matter is that these robots are still not really anthropometric, as much as we would like to have them. The artificial muscles that they have are not anywhere near like animal muscles in terms of their functionality and robustness and all of that. So it is very challenging to build robots that are anything like the human body, and of course the human mind, which we don't really understand fully yet. So what seems to me to be more feasible today is to build virtual robots to simulate the human body and the human brain in a computer in a way that's much more biomimetic, imitates the biology much more closely than any physical hardware robot can do today. And that has been really the theme of my work in this area. Build virtual humans that are as realistic as possible, and then experiment with them, and develop AI algorithms and all of that in the context of these simulated virtual humans. So this is much more possible today because computer graphics has made major strides in improving realism. So just like that image I showed you earlier here on the left, we also have here another image. You have to look closely at it to decide whether or not it's actually a photograph of a real person, or whether this is a computer model, a graphics model of a human head. And of course, one could say this is merely computer graphics, but the fact that and of course, the graphics that I've shown you so far, these virtual characters that are depicted are not autonomous characters, and they're certainly not intelligent characters. So it is kind of merely computer graphics, as you can kind of see here. But computer graphics is this very fascinating field that tries to encompass everything, all kind of all natural phenomena, not just the physical phenomena of the world around us, but also the natural phenomena of the animals, plants, and humans that are in this natural world. And so computer graphics in the large sense of the field has to deal with artificial intelligence and perception, so computer vision, mechanics, physics, biomechanics, and biology, how biological evolution works, and all of these things. So basically, computer graphics can be thought of in the large as being a field that encompasses all the other fields of knowledge. So in that sense, it's very important. And so I'd like to distinguish then that the kind of computer graphics that we do in my lab tries to simulate reality as much as possible, and not just in terms of the appearance of something, but also in the functionality of something, how something works, like how a human works, for example. So let me show you the first video here, which is the one on the right, and look at it, and hopefully it plays. Rita, please let me know if this doesn't play smoothly enough, and maybe I can compensate for that somehow, but
Yeah, sure.
let me know how it looks.
Sure.
And there's sound on this. That looked a bit choppy even at my end, didn't it? It wasn't a very smooth playback. How did it look over there?
They actually look like really look like so that one is actually a simulation of human.
Well, no, but I'm just asking you, how does it look in terms of the playback of the video? Was it choppy type of playback, not smooth, or was it kind of smooth
Understand said
animation.
it was choppy for him as well. So it is a bit choppy, I think. Yeah.
Yeah, that's, I guess, bandwidth issues. I don't know. Let me see here. Page. Okay, so yeah, I just popped up my chat window here, and Alexander says it was choppy for me as well. So, well, but I hope you could see the realism in that, how realistic it looked, and you have to watch it for a while and of course you realize that it's not it's not a real, it's not live video of an actual person. It's computer graphics video. Um, so and it's computer graphics, but the animation was done by hand. It was done by an animator, a real person. In fact, the model was created by a trained modeler and animator. And the realism is because that you know uh, person spent a lot of time in making the motion and everything, so it looks realistic. And so it was basically done by hand. Is the key message here. And so what we're trying to do, and what I'm going to be showing you today, is trying to be as autonomous as possible. Everything that I'll be showing you will be simulated, and all of the virtual humans or parts of virtual humans will be simulated naturally and will happen without any human intervention, really, without any person doing the animation. So if anyone has questions, please put it in the chat window if you don't want to speak out loud so I can hear you. So let me take you on this journey then about modeling humans and human control, starting with what got me interested in human simulation, which actually dates back 3 decades now. And it was modeling and animating the human face. And unlike the face model that you saw in that video, the human face is not a simple surface with a texture on it. It's a complex biomechanical structure. It has it's covered by skin, and the skin is not a surface, but it's a multi-layer sandwich of various soft tissues. There's the epidermis, the dermal layer, fibrous septum over here, which has fatty tissue and vessels and so on. There are muscles embedded in the soft tissue underneath the soft tissue of the skin, and beneath that as well is additional fatty or adipose tissue. So this is a complex biomechanical multi-layered structure, and the face is actuated, as shown here, by facial muscles. These are the muscles of facial expression, and there are lots of them, and they have different Latin names, which you may be able to see around over here. So these are artists' sketches of the anatomy of the face. And what we want to try to do, or what we have tried to do in the past, is model this to a reasonable degree of accuracy so that we can build simulated faces that work on their own. So now the muscles are attached to the skull, which is underneath. Some of the muscles are attached to the skull, others are sort of floating around, especially around the mouth and the eyes and so on. But many of the muscles are attached to attachment points in the skull, which is an impenetrable surface. So the soft tissues of the face lie on top of the skull and deform according to muscle contractions. So as I said, 30 years ago, we started building this physics-based model of the face, which had various levels of simulation and control. So the face can the simulation of the face renders images. So through the graphics pipeline, which creates video of the face in action, but the facial geometry is what gives expression. The deforming of the geometry of the face we recognize as human expressions. And so we want to be able to deform the face in a natural way. And the natural way to do this is by doing physics or biomechanics, where the muscles of the face deform the tissues, the synthetic soft tissues of our face model. The muscles contract. That's what muscles do. They always contract. And so they exert forces on the soft tissues of the face. And if you can control the muscles, the actuators, the facial actuators, if you can control them in a proper coordinated fashion, then you can create facial expressions. So at the level of expression, then you have, we have a higher level controller, which is known as facial action coding system, which was developed by psychologists who study the human face. And this level really is what coordinates the actuators in the model to produce meaningful facial expressions. So more about that momentarily. Now, to construct this face, we use physics principles. So we create a model of the skin, which is a multi-layer model that you could see here. And embedded within the skin are actuators, which are shown here. You can see a little one coming over here, which is a straight line. Again, more about that later. But the layers of the skin here are built in a discrete finite element model with an epidermal layer and then a dermis fatty tissue layer and a muscle layer underneath. And remember, this is 30-year-old work already, but this is a simple model of facial tissue, and it's a mechanical model that could actually deform. So with the proper placement of the facial muscle actuators, so here we see about 3 dozen facial muscles. There are many more in a real person's face, but here we have 3 dozen of them in anatomically correct positions and various different muscle groups. And when they're positioned within a proper geometric model that kind of has facial shape, then you can create a model that actually works. So here, I guess this is a bit choppy as well, perhaps, but you can see here, this is a face model that actually works on its own. It's just producing random expressions of random intensities, but you can see behind it, if you look behind, you can see the muscle actuators working in coordinated manner to contract. They contract and they deform the skin, which is this triangulated finite element structure. And the deformations we interpret looking at the outside as facial expressions. And you could see, this looks a bit strange because it's random facial expressions, but you could see natural things like the laugh lines, nasolabial furrows, and so on. But the important thing about this is that the model works on its own, and this is actually working in real time. It's simple enough, but at the same time complex enough that it can produce its own facial expression and its own facial expressions completely autonomously. Okay, so Alexander says, have you tried other geometries such as tetrahedrons to see if they're not? Well, yeah, we tried different geometries, but we converged on this prism, basically, because of the layered structure. So we wanted triangles and various layers. So this prismatic structure was the one that seemed to work best for us. But since then, many people have looked at, in computer graphics, have looked at facial animation and so on, and there are other types of models that are out there today. And of course, the models that are being used in movies and professional situations have gotten quite complex and fairly realistic. But still, it's very difficult. They look realistic when they're not moving, but when a human face starts moving, when a model of a human face starts moving, starts animating, then humans become very critical about it, especially when it looks realistic, when it's standing still, like the original one that I showed you looks very realistic when it's still. And so when it starts moving, you have to be very accurate in the motion. Otherwise, people get, they get weirded out by the whole thing. If you know what I mean. In robotics, this is called kind of the uncanny valley, and in computer graphics, the so-called uncanny valley, where something looks realistic visually, but when it doesn't move realistically. So it's like a really realistic human face that doesn't move exactly right. It looks very strange and repulsive, and that's because we're all experts about how human faces look and move. So when there's an imbalance there, it doesn't look good at all. That's the uncanny valley. Okay, so this structure over here seemed to work very well for us, and it's different sizes of triangles depending on which part of the face it is. The very articulate and highly curved parts of the face require more triangles or smaller triangles, and then these parts can be bigger. But then there's a subdivision surface underneath here, which gives you a smooth surface as well. But the biomechanics of it is such that it works naturally, just like it does in the real world. Now, as I said, people have worked on simulation. So this former postdoc of mine, Sifakis, who did this particular work in conjunction with craniofacial surgeon. And here, you have a better model of skin than the one we had, and this is simulating a tumor, a skin tumor that needs to be cut out by a surgeon. And so what you're going to see is a simulation of the surgical procedure where you cut out, the surgeon cuts out the defect, the defect here, and creates a hole, and then has to close the hole. And it's kind of fascinating how this works. So here, I'm going to play this for you. So there it cuts out the defect and then has to close the hole in the skin. And this is how it's done for this particular type of surgical procedure. You see it again. And this is so a realistic simulation of skin with much more accurate finite element model. But this is not real time. It requires more complex computations and so on. So anyway, so that's how that goes. And I mentioned the actuators. So here you could see the actuators in this model that I showed you, and up over here you could see the expressions. So the 6 expressions, natural expressions that everybody pretty much everywhere around the world has: joy, anger, surprise, sadness, disgust, fear. And so this is kind of the expression space, if you like, a 6-dimensional hypercube, and you can go from neutral to maximum in each of these dimensions and everywhere in between. And then you can also rotate the jaw and so on over here. And that creates various different muscle combinations. Some expressions can be asymmetric as well. And you can kind of see, over here in this panel, you could see combinations of anger and surprise and sadness and disgust and fear. And this is kind of like the expression that comes out from a combination of all of these, and so on. So that's sort of the different levels of control in this model. So that's sort of our early work from my group in human facial modeling. And you'll see this face again later in the talk, but let me kind of move on to the body then. State of the art today in motion pictures and games is motion capture technology. And I'm sure many of you know this. have seen it. Basically, you put a computer vision system to work on the human body. You know, the way it's normally done is you have the actor wear a tight bodysuit like this with retro reflective markers normally placed at the joints, and then you have a high-speed camera. I mean, here, high-speed camera over here with infrared light that bounces off these markers and hits multiple cameras. And through computer vision triangulation, you can position these markers in three-dimensional space with proper calibration and everything be done. So these are high-speed cameras, and so you can track these markers and fit an articulated skeleton, skeletal structure, and then interpret the positions of these markers in terms with inverse kinematics, interpret these in terms of joint angles of the joints in the body, the bones. Like you saw bones earlier, where the hand was kind of being animated. If you remember, if you notice that there were fingers with bones in there. So really, you want to get the joint angles of the human body over time. But this is just essentially recording off of a real actor, a real human body. So this is Andy Serkis, the actor who animated the body and the face of Golem over here in the Lord of the Rings movie trilogy. So it's essentially motion capture. And here in games, you've got Tiger Woods over here doing golf swings and other athletes pitching and baseball. And you know, this is how they capture motion, essentially to animate game characters. And this is essentially recording motion, and just like recording sound from real humans, and then playing this back. And you could do some signal processing and all of that to create, to modify the movement to some degree and all of that. But it's basically recording and playback. It's not what we're trying to accomplish, which is autonomous self-control, self-animation. We want self-animated virtual humans that animate themselves just like we physical humans animate ourselves in our physical world. So what was the state of the art about 20 years ago in animating humans in computer graphics? So this was it. Essentially, we had human anthropomorphic type of skeletal structure with joints. And basically, this was being actuated by torque motors, rotational motors around each joint. So virtual motors around each of the rotational degrees of freedom of each joint. And in the body, we have three degree of freedom rotations, say in the shoulder, essentially 2 degree of freedom rotations on elbows, and so on. Each of the joints have different numbers of rotational degrees of freedom. And so we can put these virtual motors in there and then simulate this structure in gravity with ground reaction forces. So there's physics over here in this articulated structure, and it's contact with the environment in which it's situated. And then the task is how to control the actuators. So basically, what signals to send to the actuator, just like robotics. In most robots, you have rotational motors, and you have to send currents to the motors in order to actuate the robot. And so this was how it was done 20 years ago. That was state of the art also in computer graphics, to do things that way. So I'm not going to get into the details of this. I just want to show you some examples. So here we have this articulated skeleton diving down the stairs. So you can't. This is not motion capture, obviously, because you wouldn't want a person to do this in order to capture the movement, because it's going to break his neck if he does something like this. Very dangerous. So this is physical simulation. So this is kind of like a virtual stuntman that can go through all kinds of dangerous situations and torture and not care. So but there's some very interesting control problems here. like, you knock this skeleton over, and he has to get back up again. And here he's doing it on his own, just like the face was doing what it was doing on its own, self-animating. Here, this virtual human is animating itself and can control its balance in gravity. You saw its strategy. It rolled over, got into up on hands and knees, and finally tucks its feet under it and rises up and balances. So this is an early example of a virtual human that can animate itself in a completely autonomous manner. And it's done through physics simulation and control algorithms that in this instance were very much like robotic control algorithms. And the complexity of this is similar to the kinds of complexities that people working in robotics face when working with real physical robots, because the physics simulation is relatively accurate. So, well, what's missing in this, of course, is muscles, right? And you can see here the muscular system of the body, again in this artist's drawing, and look at the complexity of this. It's extremely complicated, and muscles are not like motors. They're not rotational motors, as you saw with the face model that we had. These are contractile actuators, usually acting in a straight line, although sometimes, in the face, they could act around in a circle, like around the mouth to contract the mouth and so on. But here, the skeletal muscles are mainly point-to-point muscles attached to different bones in the skeletons across joints. And so the challenge here is how to model the muscles of the human body, model them anatomically accurately, and then be able to control these hundreds of muscles in the human body such that the body can perform motor tasks, natural motor tasks, the way humans do. So, well, we can start by looking at the muscles, the skeletal muscles. So as we know, skeletal muscles actuate the skeleton. So here, usually these muscles come in pairs. You have agonists and antagonists, or flexors and extensors, as they're called. And so they work in pairs. Here you have the bicep and the tricep muscles, and they're connected to bones through tendons and so on. And one extends the arm, and the other one contracts. The bicep contracts the arm, or flexes, and the tricep extends. So these pairs are found everywhere in the human body, and that's part of the biology. Now, looking at the muscles themselves, each muscle is very complicated, right? And one can spend a lifetime studying a muscle, and many people have. And but here you see a diagram of a muscle, and you could see the parts of it. And you got the tendon over here. Then you have the muscle body, and the muscle body is composed of fascicles. In here, many fascicles. Each fascicle is composed of muscle fibers, a bundle of muscle fibers. And then each muscle fiber is a bundle of myofibrils. And each myofibril finally is many sarcomeres over here, which are basically the motors, the contractile motors of the muscle. And here's where you get down to basically the proteins that compose the muscle. And you've got over here, you've got actin and myosin proteins that, when they're activated, they basically pull against each other, and the whole muscle contracts. So muscles cannot extend; they're elastic. So when they relax, they extend to their natural length. But when they're driven by efferent uh, control signal from a motor neuron that controls the muscle, basically what they do is they contract. So they apply forces through the tendons to the bones in this way. So that's a muscle, and it's it's challenging and difficult to actually model this in full detail. So we want to get to a right level of abstraction here so we can model the muscle reasonably accurately, but without just getting into a level of detail where we can never get out of it so deep. So we appeal to this so-called Hill muscle model. And Archibald Hill was, you can see when his lifespan over here, he won the 1922 Nobel Prize in Physiology and Medicine for really studying mechanical work produced in animal muscle and coming up with he came up with a simple model of muscle, which is still, fairly reasonably accurate, which is called the Hill the Hill muscle model. Excuse me. And here you can see the muscle model. It's composed of series and parallel elastic elements. So these are SE, series elastic, and PE, parallel elastic, or series element, parallel element. So you can think of them as springs, simple springs, elastic springs, according to Hooke's law, basically, or could be non-Hookean as well, but some kind of elastic type of response. And then there's a contractile element over here in series with the elastic element, and that is what actually produces the muscle contraction. And this is activated by a signal. I'll refer to these signals as A. And so this is the activation signal of the muscle. When signal comes in, the muscle contracts. Okay, so basically the total force that the muscle produces is part of the active part, the active contraction, plus the passive elasticity of the muscles with the series and parallel element. And that's the total force here. So you can see, for example, this is given in terms of the ratio of muscle, the natural length of the muscle I0 versus its actual length. So this is lambda, the ratio of those two. And so the muscle basically, the response in this way is a combination of the active part over here, the blue, and the passive part, which is kind of like an exponential spring over here. So the total is this dotted line, which is what the force of the muscle relative as a function of lambda kind of looks like in the Hill model. So we use a simplified version of this, or have been in the past, which is a linearized version of the Hill model. So we have the passive part over here, as before, the exponential elastic part. And then the active part is a linearized version of this, which has a different slope depending on the muscle activation. So this is kind of like a stiffness. The slope here represents the stiffness of the muscle, and the stiffness depends on the activation coming in. So high activation means high stiffness, high slope, and lower activation, lower stiffness and lower slope. But these two parts kind of add up together as before, and you get the total force. And here you can see some equations of that, but hopefully it seems like intuitively, it should be intuitively meaningful in terms of the words that I'm using here. If you have any questions, please try to, yeah. Are there any Hill models for agonist, antagonist muscle pairs, such as bicep, tricep muscle? Well, what we're doing is actually modeling each muscle individually. So then we will put these Hill type muscle models together, one for agonist and antagonist. You'll see that coming up. and they'll work in pairs. So that's how we're going to model all the muscles of the body. So here, for example, we're going to put around these two bones, we're going to put these two muscles, and this is how the body can control the stiffness by co-activating the pairs of muscles. So for example, if I don't know if you could see this, here's my arm, and or my wrist over here, and I've got pairs of muscles on both sides of the wrist. So if I want to, this is a very limp wrist over here, right? If I deflect it with my hand, it deflects a lot. But I can stiffen my wrist by co-activating the muscles on this part with the muscles on that part, and now I've got a stiff wrist. And I push it, and it doesn't move. So, in the same pose, a limp wrist moves. In fact, it sags under gravity. But a stiff wrist, straight pose, doesn't. And this is with co-activation. So how to do this is still kind of a somewhat of a mystery. It's still kind of like an open research problem, but we were able to do something reasonable by well, I can't really get into the details of this. I shouldn't, because it's going to take too long, but you can kind of get into the null space of this muscle pair, and then essentially think of it as, if I want to maintain this pose against gravity, what should the activations of the muscles on each side of my wrist should be. But then, if I want to stiffen it, I just want to take that same ratio of muscle activations and just kind of jack it up in intensity, and then you get high co-activation and a stiff skeleton as a result of that. So anyway, let me move on to modeling something quite complex, which is still just the body part here, but it's the so-called cervical cephalic complex. So this is the head-neck subsystem of the human body. Now, if you look at the anatomy of even the neck, you can see the complexity of the muscles in here. It seems like biology is sort of perversely complex. It tries to, in a sense, evolve very complex biomechanical structures. In robotics, one tries to reduce complexity because our artificial motors and parts break down. So if you want to maintain a system that works robustly, try to make it as simple as possible to get the job done. But biology kind of works the opposite way. It tries to, in a sense, maximize complexity and uses that very, very well, because it's highly flexible with many joints, many muscles. You get great motor skills, that come out of it, complex motor skills that robots are really incapable of doing still. And it would seem that it would be very difficult to control systems like this that are very complex. You know how difficult it is to control even somewhat simple robots or simplistic robots. What about something like this that's very, very complex? It would seem almost impossible to do. But what I'm going to show you is that it is certainly possible to do if you take the right approach, which is the biomimetic approach, how the human brain does it, we think. And so if you take that approach, then it's certainly possible, and the complexity actually helps you in maintaining stability and control. So having multiple muscles, redundant degrees of freedom of articulation in the skeleton really assists in controlling rather than hurts you if you take the right approach. So that's sort of an important message here, which is different perhaps than what many robotics people might think, well, perhaps philosophically. But anyway, let me not get too much into philosophy and try to show you as many results as possible. Okay, so here our next step basically was to try to model a part of the body, the neck, as accurately as possible and make a control system that could actually work just for the neck. So here you see the skeletal model, and you can see that here, it's anatomically accurate in terms of the bones, and you have here 7 what are called cervical vertebrae, which are the 7 vertebrae, from the down here, which is the torso, to the base of the neck over here. You can see like this one over here rotates around. See, there's this bone piece from the second vertebrae, the blue one that's coming up, and then that fits into the top vertebra, and this is called the no joint because it helps you do this. No, no, rotates the head side to side. And then the one below is the yes joint because it does this with the head, and then saying yes, yes, yes. And then the others are basically a flexible multi-joint pendulum upside down like this. And there are discs between the joints, which are flexible cushions. And then, of course, there are all the muscles. So anyway, these are just the bones here. Now, here's the skeletal model. And as I said, 7 cervical vertebrae and a skull, all coupled by 3 degree of freedom joints. So three rotational degree of freedom joints in between these vertebra. And then ligaments and discs holding this together, which is sort of the passive elasticity of this column, flexible column. And then you can model the equations of motion of this. This is just Newton's laws of motion. This is mass time. Q over here is just the rotational degrees of freedom of this whole structure. So that's in the vector Q. Then M is a mass matrix, which depends on Q. Q double dot is the rotational accelerations, Q dot the rotational velocities. And so here you've got the mass, the gravity, Coriolis, and passive elastic forces are in this term over here. And if you turn on the simulation, of course, the whole thing collapses in gravity, just as it would. If you somehow fell asleep, your head would just collapse in gravity. And so we've got to have the muscles over here of the neck modeled. So here we see the muscles in our model, and I'll explain these in a little bit more detail in the next slide. There's a moment arm matrix here over here, and then muscle activation forces over here. But what's driving the whole thing is a set of signals that are sent to each of the muscles. Okay, so what we need to do is figure out how there are 72 muscles in this model in 3 different layers. You've got the deep muscles, which are 48 muscles close to the vertebra that hold them together, short, deep muscles, and these longer muscles here are linear or sort of a series combination of actuators, hill actuators, and then the 12 longer intermediate muscles, and then 12 more superficial muscles on the outside, which are essentially going from the shoulders up to the base of the skull. And this is anatomically accurate, although it's a reduction in the number of muscles from the real neck, but still quite a large number of muscles here that have to be controlled. So our challenge was how to co-actuate and control this head-neck subsystem so that it produces, so it can control itself. So you can balance the head on top of this flexible column and not lose control and have the head flop, but also to make control head movements in gravity, to be able to look at things and so on. So all of that is kind of challenging. So we did this piece for the annual computer graphics conference in the year that this work was done. And it's kind of a humorous piece that in about a minute, 1 minute shows you how this model works in a funny way, in a humorous way. So I'll play this right now. Wow. So that was our teaser. But you can kind of see our model next to a sketch by Leonardo da Vinci back in the 1500s, where he was obviously studying the anatomy of the human neck. And, that was his sketch of the muscles, the primary muscles in the neck. You could compare that to our model, how it looks. And as I said, each of these lines over here represents a Hill contractile actuator. And so these need to be controlled. And as the video mentioned, trained neural networks are what's needed to control this. So before I show you that, let me just show you kind of a system diagram here. We have the biomechanical face model that you saw before, but there's a skeletal system, of course, the skull plus the cervical vertebrae, and then you've got the muscles of the neck that control the neck and can actuate the skull. And then you've got proprioceptive feedback coming from, there's proprioceptive feedback in the body that gives information to the brain about the pose of the body, the velocity, and so on. So you want this kind of information coming back to the controllers. And what we have is two levels of control, a low-level reflex controller and a higher-level voluntary controller. So the voluntary controller is the controller that the model can use to voluntarily move its head. If I want to look at something, I voluntarily move, control my muscles. My brain controls my muscles of the neck so I can rotate my head to look at something in front of me. So that's the voluntary part. And the reflex part is the part that sends the activation signals to the muscles. And there's a smaller strain rate feedback loop over here, but the reflex controller sends the muscle activations finally to accomplish what the voluntary controller wants to do. So there's a feed forward signal, set point signal. I don't want to get into the details of this, but ultimately the activation signals that are sent to the muscles really drive the muscles to contract. Now, the contracting muscles produce forces against the bones, pull the bones together, and that is what actuates the articulated skeletal structure of the neck. And then, of course, the whole system is embedded in a physically simulated environment with gravity and external forces and so on. And the whole thing works within that virtual, physics simulated universe, which changes, this changes the head pose. And of course, the biomechanical face moves along with the head. So what I want to look into next is how these controllers actually work. And, this is kind of the tricky part here. And this has been our challenge. And we decided that neuromuscular control was the answer here. We had to do it the same way that the brain, hypothetically, is doing things. So let me explain to you very briefly how we can get a system like this to learn to control itself. Just like real humans learn to control their heads and their necks. A baby can do this. Well, a growing baby eventually gets the ability to control its neck so it can look around, and do all of that. How does that work? How does the brain do that? The baby knows nothing about physics, really. The brain knows nothing about physics, Newtonian mechanics, anything like that, or control theory, or anything like that. So how could it possibly work that the biological neural networks in the head can actually learn to control the body, the complexity of the body? So this is sort of a simplified way of doing that, we think, but still, very much biomimetic. So let's suppose we take our head model like this and we put a visual target, this little doll. I mean, think of this like a baby, if you like, and we put this little doll in front, somewhere in the in the sort of optical space of the baby, the space that he can look at. And what we want to do is have the baby look at this doll over here. So how do we do that? Well, this is a random target pose. And so let's suppose we rotate the head like this in the proper orientation. So now the nose is facing the doll over here, and the head is looking straight on to this visual target. So this, we can compute what are the lengths of all the muscles in the system right here. What are the desired lengths to achieve this pose? So this is very easy to do. And then we can compute, if you inverse kinematics, compute the desired joint angles of all the vertebra, all the joints going up the neck over here. So, but remember that this head is in gravity. So gravity is pulling down. That means that the muscles have to exert forces on the bones in order to keep the head in that pose despite the downward pull of gravity. So now this is not just an inverse kinematics problem, but also an inverse dynamics problem. We have to be able to compute what are the muscle activations required to produce the muscle forces that hold the head fixed in that pose against gravity. So this is inverse dynamics, and this requires an optimization process to be solved in order to determine what the muscle activations are. A nonlinear optimization problem, and you can do it, you can solve it here through numerical methods, but it's going to take quite a bit of computation to do that kind of thing. But the reason we want to do this is because we want to synthesize training data for our model. This is a way of actually synthesizing information that the model can then use to train itself, to train the neural network controller so that it can do this automatically and very quickly after it's been trained. So this synthesis is done offline. Now in the real world, the synthesis is done online by the physics of the world. And so we're constantly synthesizing training data for our brains by just doing things in the real world. And because physics operates in real time in the real world, we get real-time feedback and we can do it. But here in the simulated world, we can do it incrementally, where we solve incremental inverse kinematics and inverse dynamics problems and so on, incrementally, and generate arbitrary quantities of training data that can then be fed to the model so it can learn how to control itself online and in real time. Okay, so what we want to do then is put this doll in many, many random positions around the visual field of the model. So let's say 20,000 random positions like this, random target poses, and solve this incremental inverse kinematic IK or inverse dynamic ID problems each time and generate training pairs. So what this is doing for us is, if it says if we want to be in a particular pose with the head, some particular orientation with the head, then these are the muscle forces that have to be for that to achieve that particular pose against gravity. So what we're doing for all of these, let's say 20,000 random positions, is generating input-output training pairs. The input is the desired pose. The output is the required muscle signals, activation signals, to send to the 72 muscles in order to achieve that pose, right? So these are the training pairs that we do. And so we feed this to a neural network. We all know what neural networks are, I presume. And what we have then is, in a high dimensional space, we have scattered sparse training data like this, right? So these are target poses in the x-axis over here and muscle activations in the y-axis. The desired muscle, so the desired target poses, which we've actually put here as samples, and then activation. So this is two-dimensional here, but remember, it's happening in a high-dimensional space. So what the network does, a properly trained neural network will be able to generalize without overfitting. We'll do proper generalization, and basically it's a regression problem, right? So the trained neural network will hopefully give us something like this that regresses the training data, and then once this is done, then we can interrogate the trained neural network anywhere in between examples. So these are the training examples, but you could figure out good activation signals for the model for any target pose continuously if you do it like this. So that's the function of the neural network. And lo and behold, if it's done well, then the model is able to control itself once it's trained in real time and can visually track the moving target. The expressions you see here are just, automatic expressions which depend on what the target is doing. Like here it's shaking and he's unhappy about that, or, happy, or kind of like a surprised expression there, depending on what the model is doing. And then, what you saw earlier as well was sort of three of these together, which are doing sort of nonverbal communication with one another. Think of it kind of like a conversation, but where they're not speaking, they're just making faces at each other. So this is the leader over here, and then followers on each side. And when you're doing a conversation, you want to include other people. So you don't want to just look at one person and ignore the other person normally. So they're doing some behavioral response here, simple behavioral response that's kind of natural. Okay. So the problem with this approach, when we did it about, 15 years ago or something like that, now, 20, maybe more like 20, is that these were shallow neural networks back then. Deep learning hadn't been invented yet. So that breakthrough hadn't come yet. So the problem was that even with this simple model of the neck, it was kind of overloading these shallow neural networks. And so the problem is that, let's say, in this simulation here, we're rotating the shoulders. So if we train this system with horizontal shoulders, body pose, and then we rotate, then it falls out of its training range and collapses. The model cannot control itself anymore. And the reason for that is because the neural networks got saturated by all the training data that we give them and basically could not learn anymore. So thankfully, deep learning was figured out by machine learning people. And then we were kind of the first, in a sense, to start using it, to use it in computer graphics. We were the first to use shallow machine learning, shallow neural networks in graphics, and we were sort of the first to use deep learning in this kind of situation in computer graphics as well for control types of problems. And we started by using stacked autoencoders, something like that. This was in 2015. Even with that simpler type of deep model, the system can now control itself in multiple poses. So you basically have to train it for various body poses as well as for head orientations in a particular pose. So it increases the complexity of the model quite a bit. But you could see much more stable and robust control using deep neural networks. So with that, then that was a big success for us that we could actually do this. And so we said, well, let us tackle the complete body. Let's just boldly go, where no one has gone before, so to speak, and then control the full human body using this same approach and see if we can do it. And that's what we've been working on basically for the past decade plus. So let me, in fact, we had this model back in 2009, a full model of the human body, but we didn't have the ability to control it. And so the remainder of this talk will be about how deep learning can be applied in a clever way, we think, to be able to control the full human body model. And so here, this body has 75 bones or 165 degrees of freedom, excluding the hands, a large number of muscles, 846 muscles. This excludes the facial muscles. It's just the muscles of the skeletal muscles of the body here. But you can see there's a large number of muscles. Also, a volumetric finite element soft tissue model with 350,000 tetrahedral finite elements, and full accuracy, anatomical accuracy of where the muscles are positioned and all of that. So well, I've gone a little bit more than an hour, so shall I take a break at this point or continue talking? And
you can actually take a break at this point because it's like more than an hour already. Because
okay.
I found that you have a lot of like very informative, and then so that you can actually take a break first, and then we
Okay.
start afterwards. Yeah.
So how long of a break do you want?
Well, it can be like as an original setting is like half an hour,
Okay, and then
or anything that you like. That's great. Yeah.
well, I think I'm going a bit slowly. How much time do I have after the break then?
Well, that would be like less than an hour, but you can actually just according to your schedule and according to your content, make it according to your
Okay.
content. That would be fine.
Well, maybe, is it okay to take like a 15 or 20-minute break and then?
Sure.
Okay.
As you like. That would be
So
fine.
let's do 15 minutes and then
Yep.
yeah, I'll be
Yeah.
happy to continue.
Thank you.
Okay. Okay.
Thank you.
Yeah, you're welcome. Okay.
So everybody, we are now having a short break. So for those who joined lately, may I introduce the project again? The project is a IIDS artificial intelligence and ubiquitous studies, and then we have invited a lot of the speakers in this year. And then we will also have got we actually have got a call for paper for this event as well. That's like AI and ubiquitous studies. So if you have got papers to submit, etc., just let me know as soon as possible. So we would like to collect all the book chapters by the end of January. So just let us know by the time that you have got some ideas. So if you have got some ideas, you just send me an email, and then to drop me an email. And of course, that we have got some other events as we have got some other call for paper as well. So and then I will show you up. I will show you later on. And then in the meantime, please help us to fill the I will send you the link for like evaluation, and then please help us to fill a high marks for his talk, and then if you would like to introduce if you would like to introduce yourself to everybody, please also either turn on your mic, okay, and of course that you may also do some other way around as well. So just do feel free to chat with one another, and of course you can also share your name cards at any time. So I'm Dr. Rita E. Manley from Hong Kong Xi'an University, is actually the host of this whole series of events. And then our major aim is that hopefully that we have got some collaborations between like speakers, attendees, or some other people's. And then if you have got any sort of idea about like what kind of things that you would like to talk to, okay, thank you, Gabriel. You would like to talk to, that you can just let us know as well. So Gabriel, I think you have got a event tomorrow, right? So you can actually share your materials to the rest of the group so that they can attend your events tomorrow as well. And so as the events in the afternoon. So Gabriel is actually another speaker of today in the afternoon. So Gabriel, you can actually share the materials, or even you can turn on the mic to talk to them. Okay. In the meantime, please help us to fill a very high mark for extremely high mark, extremely high mark for our presenter speech today. So I would like to share the call for paper of mine. So we have got a safety science, a spectral issue. That's an AI and smart cities implication on urban safety. So this one is an impact factor of 4.105. So it is a smart issue. This is a spectral issue together with the editor-in-chief of the safety science. So if you have got a topic, then you can just let us know. And then we have got some of the aim and script that is like later here. So it's about like AI. AI is there are a lot of things for which like it is like just coming to the scene, like for example AI robots, and then we have got like some other AI products. But then the question is that we are not sure about the safety issues. So we try to talk about like the bright side and dark side of the AI and smart tools on safeties, but but not limited to like for example ubiquitous or smart tools usage, safety concern, AI robot safety, implications of on the built environment, AI safety for education and training, smart home safety, smart city safety issues, smart or AI tools and safety. Okay, and then so these are some of the items for which we are calling the paper, and of course we have got some other items. So we have got like state-of-art research in AI and ubiquitous. So we are calling for papers and we are calling for book chapters, and hopefully we will be able to receive like in early 2021, so that we will
Actually,
have.
we cannot see your screen.
I cannot see the screen. Oh, sorry. Okay. So can you see the screen now? So just let me know if you cannot see the screen. So
no, we cannot see the screen yet.
Cannot see the screen yet?
Yeah.
Yeah, I've already clicked the share screen already. So can you see the screen now?
No.
Your screen?
It's strange.
No, it's demented screen.
I think he has to stop sharing before we can see yours.
Yes.
Yeah. Sure.
Okay. Let me stop sharing.
Yeah.
Okay. Thank you.
So okay. So just a bit of the information. So can you see it now?
Yes.
Yeah. So there are like we have got the AI and smart cities on the urban safety. So there's a safety science spot issues. So that one is like impact factor of 4.105. So it covers a few of the special issue topics, like for example, AI robot safety, AI implications on built environment, AI education safety training, smart home safety, smart city safety issues, smart or AI tools. And then the important days, there is like open submission 1st of January, submission deadline 30th of April 2021, and final acceptance days as 31st of October 2021. So feel free to submit it. And then we also have got some other book chapters, and then we have got state-of-art research in AI, which is Spring Up book chapters, and then Spring Up book and construction safety. So you just email me if you have got any ideas, and then other spectral issues, etc. So you can actually check for the call for papers. And earlier, and then later in the afternoon, we have got a section for Gabriel's presentation for today. So you may be able to see in the chat box earlier. So after the Demetrius talk, we have got Gabriel's talk and also Patrick's talk as well. So if you have got some idea about like moving up to like PhD degree, you can also send me email later on. So thank you. So for the Demetrius, if you would like to start, then you can just start at any time that you wish.
Okay, good. Yeah, I am ready to go again. Turn on my video here. And then share my screen again. Which one is it? Can you see my screen again?
Oh, yes.
Yes.
Okay, very good. Somehow I lost my chat window here. Oops. What happened to the chat window? Okay, there it is again. All right, so there were some questions here, I think, perhaps. Alexander asks, is there only one possible pose you looked at for the situation, or is it more of a manifold of options? Did I answer that question, or it's a manifold? Yeah, it's a high dimensional manifold that we're trying to sample here. The more samples you have, and if assuming your network can learn, is deep enough that it can learn from all the training data that you can provide, because you can provide arbitrary quantities of training data, just like the natural world around us provides our brains with arbitrary quantities of training data, and we learn how to control ourselves and things around us through the neural networks in our heads, basically, without any knowledge of physics or anything like that. I mean, really, we don't have Newton's laws of motion embedded into our heads in any way. We can't do optimal control in that sense, but we could certainly learn from training data that's synthesized for us by the physical world around us, and learn by doing, basically, which is the same approach here that's being used. So is that a reasonable answer to the questions, or is there anything else?
Yes, I have got some questions. So which is
Okay.
actually related to your talk, and so as like like for example, like what actually maybe the latest development trends, prospects and challenges in AI. For example, that you have mentioned about the muscular stuff, and then try to simulate the human body, for example. So in your own research, so what may be the trends, prospects, and also challenges in AI you just in this area?
Well, yeah. Maybe I could try to answer that at the end after, because I've this is still sort of at the middle of the talk, and there's stuff that we've done much more recent, in fact, very recently, that is part of this presentation towards the end. So if we can hold that off for another 45 minutes or so, then you can see a lot more here. But I should mention that a lot of this material is something I gave as a keynote address to the ICRA conference last year, while we were still able to travel to conferences. So that was a keynote talk that I gave there, and so I think it's pretty much cutting edge stuff, even though it's not physical robotics, it's virtual robotics, and
because we are doing like physical robotics, but virtual robotics is also something for which is like very, very interesting.
Right, and you could use virtual robots to train physical robots and all of that, which I'm not really going to have time to get into today, but that's also possible. I mean, if you have a good physical model for if you have a good virtual model for a physical robot that exists, then you could synthesize training data through the virtual robot and apply kind of the same approach to train the physical robot, potentially.
Right. Because usually we do simulation before we actually put into like more than $1 million of robots, right? So
right,
usually,
exactly.
Yeah, right.
Well, I mean,
otherwise, if it crash, then the robot will be gone.
Right. So I mean, we were doing simulation of animals, before humans and all of that, like fish simulation and stuff like that, fish motion. This was, my computer graphics work, basically. And back then, in the 90s and so on, it was, I mean, the robotics people were not taking this stuff seriously, I would say, for the most part. Today they are, because simulators have gotten so much better. And let's face it, I mean, nothing in the world happens without simulators, nothing important. I mean, pilots learn to fly aircraft with simulators. They're not going to take chances with the real airplane before they know how to fly it, on the simulator. So if a simulator is good enough, then it becomes sort of indispensable in many ways. Otherwise, you waste a lot of money, as you pointed out. So I think simulation should be taken extremely seriously, and I'm talking about simulation of the human mind as well, so that how do we understand the human brain and human perception and motor control and all that? Well, I think by building virtual robots that are as accurate as possible to the real thing, we can learn by doing, basically, by can we control this very complicated model and make it work? And if we can, that's sort of an existence proof, I would say, that it's possible. And then, okay, well, if physical roboticists can build something as accurate as the human body sometime in the future, we'll be ready for them.
Yeah, right.
Yeah, but so far there doesn't exist really any artificial muscle that's as good as a real biological, animal muscle. So I mean, people have tried many things.
Like some sort of like plastic.
Well, people have tried, these contractile metals and things like that, and to some extent they work, but they don't work as well as can produce as much force as a real biological muscle.
Right.
And so, I mean, hard to imagine that a piece of metal can do what I showed you in that muscle diagram with all of that complexity just in the muscle itself. So anyway.
Yeah, but this is like very important because, like, for example, by the time we talk about some of the robots that try to serve like those like elderly house, for example, we are having a robotic lab in my university. But then the question is that a lot of the robots look like metal, and then like the robot dog look like a kid's toy rather than that they can really resemble the real animals. And so it's like those who try to serve the elderly, for example, they look like a metal. And then it really doesn't look like a human being for which like you can just talk to, and then you think that, well, that is a human being. No, that is like by the time you look at it, that is like just like metal. And then so that what you are doing now, I think is very meaningful. In terms of like, for example, serving elderly, for example, and of course for fun, because it's like if that look like human, then probably that they can be a kind of person for which that they can talk to. They really look like human rather than just like.
Right. Yeah. There are many applications of, if you can come up with a realistic, believable, virtual human that's intelligent, then yeah, it would be amazing.
Yeah, yeah, amazing.
Well, so and I appreciate the very kind comments that some people have put in the chat there as well. So let me press on with the full human body model and how much progress we've done on that. So here you're looking at the skeletal model itself, and you can see all the bones are modeled here accurately and anatomically correct. And for this, we use the a geometric model, which was it's a commercial model that you can purchase that is just geometry basically, but it's accurate, anatomically accurate, modeled very painstakingly by experts, and with accurate geometries and everything. But we have to make it work. So we have to put in the joints. We have to put in, so this was designed for just training, medical students by, 3D virtual human that you can just fly through and look at the geometry and so on. It's known as the ultimate human, or I think maybe has a different name these days, but we use that as a template basically so that we can model everything that we do in an anatomically accurate manner. So that was like a template. Now, what's important in the human body, very important, is the spine. And we saw part of it already, the cervical part up here before, but there are many, many more, there are many more joints, vertebra in the body, along the spine. And so you can divide into three parts: the cervical part, the thoracic part over here, and then the lumbar part of the spine down here. And it's important to model this anatomical structure with full accuracy if you're going to build a virtual human that looks and acts realistically. So now if we do all of this proper modeling of the skeleton and we just put it in gravity, then it's just going to collapse, as you see here, right? Like before. So we've got to be able to put in all the muscles as well. So here you're looking at the 800 plus muscles that are in the model that I'm going to show you. We're not showing muscle in this images. We're not showing muscles on the hands, but we've got the muscles there for that as well. And we can't control them to this part, but we haven't spent too much time on hand control, manipulation, and that sort of thing. So we could still do a lot of things with kind of like kinematic control of the hands as well, so you can grab an object or something and so on. But here you see the muscle bodies, geometric muscle bodies painted different colors so you can distinguish them. And the actuators, so these are the Hill actuators, and they run inside these muscle bodies, and they, those are the ones. Just for realism, we've got all the muscle geometries as here. So by stripping away the superficial muscles, you could see the deeper muscles inside over here on the right, or the this human's left, and here as well in the back. And then if you do a proper rendering of all the muscles, then it looks kind of realistic, like the diagram that we saw earlier, the artist's diagram. And here's the skinned biomechanical model with the skin surface applied over the muscles. So this kind of shows starting from the skin and then looking translucently inside, you could see the muscle geometries. And then looking within that, you see the actual actuators that are within the muscle geometries. And if you look closely at the torso or core of the human body, you see that the core contains most of the muscles, actually. And so we're trying to model all the muscles as accurately as possible here. And so there are lots of muscles here. We'll talk about that later. And some of these longer muscles are done as series combinations of Hill actuators like that. and some of the big broad muscles, like this is the latissimus muscle in the back, big broad muscle, and it's created by multiple hill actuators in series and in parallel. Now with the skin, for the soft tissue, as I said, we use finite element methods. So we start with the skin geometry here, and we can create a lump of flesh. So this is like a lump of soft tissue that has the right constitutive property, like meat basically. Take a steak and just kind of poke it, make sure it's raw, poke it, and you could see kind of the elasticity of the meat when it's raw meat. And so that we try to model that elasticity property, so-called constitutive model, as accurately as possible. So this is a proper type of elasticity model that we apply. Again, I can't get into the details of that; it would take too long. But what we want to do is sort of cut away the outside of this lump of flesh and have just the interior. So this skin geometry acts like a cutting surface, and then what's inside is what we need. And so here we have down to these are tetrahedral finite elements, and there are actually, if we do it this way with uniform sampling, it's going to be 3.8 million tetrahedral elements, which is way too many. We can't deal with that. It's going to be too expensive. But we want to have, to resolve the curvature of the skin accurately enough. So we need fine tetrahedral elements at the surface, but inside we can coarsen the model to reduce the number of tets down by an order of magnitude, down to about 300,000 or so. So this creates the soft tissue. Now, in order to make this work in a reasonable manner, we embed the visualization geometry. So this is visualizing the muscles, the muscle geometries inside the body. We embed it into the soft tissue model. This is the physical model of the soft tissues. So we embed one into the other like this, and then the hill actuators inside the muscles actuate the bones, and then the soft tissues have the right property that volume preserving deformation that acts in the right way. As I said, we also model the muscles of the hand here. You can see that, and we can even articulate the hand to some degree, although this is not a sufficiently accurate model yet. So we're still kind of working on the hand. But you can kind of so here are the hill actuated muscles, and you can articulate. Now, here you could see, grasping two dumbbells and then doing some kind of, exercise while sitting down. And you can see how it looks on the inside. See the muscles deform, the soft tissue deforms, and the muscles deform within the soft tissue. So it looks, reasonably realistic, we think. This is a good compromise. Instead of trying to model each muscle individually and put them as a physical model individually, and then have to deal with contact forces between the muscles and so on, that gets really, really expensive computationally. So we feel this is a good compromise, which can still do. But as the title says here, this is using inverse dynamics control. What that means is if we specify the joint angles as a function of time, in other words, what the motion we want to do. So this is a sort of let's say a motion capture type of motion that we want our model to perform. We know the motion in advance, and we want to figure out what are the muscle activations that are required to make the body do that motion, which you're seeing right here. Well, with inverse dynamics, we can do that, just like I mentioned before. We can do that globally, meaning for a particular trajectory of the arm, we can solve the inverse dynamics problem for the muscles and, make that motion. But that's not realistic. That's not the way the human brain works. We don't do inverse dynamics in the brain. So we want to do a forward dynamics control, just like we did with the neck. So the basic idea then is to apply that same philosophy and approach to synthesize training data that we can have our neural networks learn from that data and then do forward control online much quicker than trying to do inverse control, which is, as I said, biologically totally unrealistic in the first place. So, but anyway, even with this, so this was before we had the deep learning approach that we can apply, but you can kind of see that the deformations of the body, soft tissues and all of that, and everything looks reasonably realistic here. And in fact, you could see here co-activation. So here, if you look, let's suppose you hold your arm in a particular pose and then you tense your muscles to make it stiff or loosen your muscles to make it floppy. What should you see? Well, here's tense muscles, loosen muscles, tense, loosen. So the arm does not move. So that's an isometric exercise, if you like, because the pose remains the same, but the stiffness changes by co-activating the muscles. So they're fighting against each other and make for a stiff, sorry, let me back up on this one. Oops. I backed up accidentally. So stiff, co-activation, and relaxed. And stiff and relaxed. And you can, so that's low co-activation or zero co-activation on the left, co-contraction, and high co-contraction on the right. So, well, our first attempt, I mean, again, this is pre-deep learning. Still, we had the model, but we couldn't control it properly. But one thing we could do is locomotion. Locomotion is actually fairly simple. It might seem difficult, but the fact that it's rhythmic, that things happen repeatedly in order to be able to walk or swim, for example, makes things simple in terms of the control problem. So first thing we did was put our virtual human in a fluid and create a virtual swimmer. And so now this requires simulation of the fluid around the body and buoyancy and all of that. And so we have our model from before immersed in a Navier-Stokes simulated fluid. For those of you somewhat familiar with fluid simulation, this is, yeah, it's challenging, but people know how to do it. Applied mathematicians know how to do this, figure it out, so we can simulate this as well with simulators that do fluid simulation. But again, the problem here is how to control the body to be able to do swimming. So we set upon the natural approach, which is known as central pattern generator, or CPG. CPGs are low-level neural circuits at the spinal cord level that actually control muscles for locomotion. You might know that certain animals, like horses, are born kind of with the ability to locomote. It takes them a matter of minutes or something to learn how to take steps, to take their initial steps, and then refine the process later. So many lower animals are just born and they're able to move around and escape danger that way. It's kind of programmed into the low-level neural circuits. And so these low-level CPGs are what produces the rhythmic actions that are required for locomotion. So here you can see our swimmer, a diagram, and what we have, okay, the musculoskeletal system, and we've got the CPG networks, which are sort of at the level of the spinal cord here, that can control muscles in the body to produce kind of the rhythmic motions of the legs and the arms that are required to produce swimming actions. So, and then of course you need a high-level controller with sensing to be able to move around in your environment and go from point A to point B, but that's, we'll talk about that later. But what are these neural circuits look like? They're basically neural oscillators. And so here's a diagram of a CPG oscillator. These are neurons, so there are very few neurons, but so here's two muscles over here, a flexor and an extensor muscle, and just a simple, rotational joint over here, one-dimensional, and you want to control these muscles so that this goes left, right, left, right. Think of it as a leg or something, and you're going to take steps with that leg. And so what these neural circuits do is generate rhythmic patterns, kind of like the one shown here. I mean, they're not perfect sinusoids, but you can modulate this, and you have control over amplitude, frequency, phase, and so on, and the waveform to some degree using these central pattern generators. So that's what we employed in the swimmer. And so here you can see our swimmer here. Just looking at the inside of the model, first of all, how it works. And
just one question. So how does it relate to, like, for the swimmer? Like, does it mean that it is a kind of like neural network simulation that's applied in this kind of like simulator model as well?
No. Well, that's a very interesting question. Can we simulate the model with a neural network? The answer is yes, can be done. I mean, we did that back in the mid-90s, early to mid-90s, where I think we were the first actually to use shallow neural networks and show that we can actually learn at least some simple models that were used in computer graphics in those days, like spacecraft, automobiles, physical models of automobiles, and the neural networks can actually learn physical dynamics from observational data. From the synthesis, we have the simulator that can simulate the model using numerical methods. We have the neural network that can observe the simulated state transitions, and the neural network can then emulate the physical model on its own, just from having learned physics, basically, but not learned the equations of motion, just learned the patterns of state transitions from observational data. So that's a pretty that's a pretty good question there. To show you more simulations here, if I can, of this swimmer. Okay, so here's a freestyle swimming. You can compare this against a real swimmer, and the frequency of the motions is timed to the real footage here, so it looks as similar as possible. That's butterfly stroke. So the model is capable of producing multiple strokes. And wait a minute, is this just playing it again? Sorry. And it could do transitions between strokes. It can speed up the swimming, slow it down, do a style transition from a butterfly over here to a freestyle right there. It does the transition very naturally. There, it could do it just voluntarily. Now I'm going to do from freestyle. Now I'm going to do butterfly. Voluntarily it does it on its own, and the physics of the model just kind of smoothly blends, if you like, the different styles in a natural way. You can also turn in water. This is like a one-arm turn. Could rotate around in the water, so it can move pretty freely. But this is a very, how to put it, ambitious multi-physics simulation here. It's very, very complex in terms of all the simulation that's going on, because you have 3 different simulators. There's one for the articulated and rigid body dynamic simulation for the bones and the skeleton. Then there's the deformable body simulation, finite elements, quasi-incompressible elasticity for that. And then there's the fluid simulation for the water, which is Eulerian fluid simulation with a particle level set method. So all of these simulators are interleaved. One takes a step, sends forces to the next, and then to the next, and so on. So they interleave against each other and we can't do it any other way. There's no one, monolithic simulator that can do all of these different regimes, from articulated multi-body dynamics to deformable elasticity to fluids. There's not a single simulator that can do all of them. So we have to have multiple simulators working together. And then, okay, here we guess we've seen that before. Just kind of showing the different layers of the bones, the actuators, the muscles, finally the fluid, splashing, and all of that. Okay, so that was our swimmer, which was a pretty challenging project. It was a PhD thesis. I'm going to show you the people who worked on this later, or acknowledge them, all my students. But as I said, locomotion is actually a simpler problem than non-locomotional, task-oriented musculoskeletal control, like reaching out and picking up something, or doing the everyday things that we do that are not locomotion based. That's kind of more difficult to do, and in my opinion. And so this has been a challenge, but our approach is to do it in a way similar to how we think the brain is doing it, by learning. Deep learning, again, is our friend because it's able to learn from all of this training data that the model can synthesize for itself. And so the biomechanical human musculoskeletal model synthesizes its own training data and trains itself. And if we can do this, type of neuromuscular control, learning-based neuromuscular control, so we can control the body, then we can tackle the bigger problem of sensory motor control, where we have to, take in sensory information and control the body to achieve some task, which is sort of the holy grail, I would say. So again, we've got our model here. To take a model like this and control it, we pretty much have to do some divide and conquer. So we want to break it up into musculoskeletal complexes, as they're called. So we've got the torso or core complex here, and that contains 443 muscles, a lot of muscles in your torso. Then we have the neck. In this model, it has 216 muscles, actuators, so the hill actuators that we have to control. And finally, the simplest ones are actually the arms and the legs, 29 muscles for the arms and 39 muscles for each of the legs, each arm and each leg. And those are the musculoskeletal complexes. And so what we do then is we devise neuromuscular controllers for each of these complexes. And the core complex ties together the other complexes, the extremities, including the head extremities, the head extremity, and the 4 limb extremities. So here we have 12 trained deep neural networks. These come in pairs because, as I said before, we have voluntary and reflex controllers. So each of these neuromuscular motor controllers comes in the pair of deep neural networks, and there's 1, 2, what am I calling? 6 of them, right? 2, 4, 5, 6, which are shown here diagrammatically. And each neuromuscular motor controller, here's the architecture of it: a voluntary and a reflex motor controller. And so here it says, okay, the reflex controller is sort of spinal level. The voluntary controller is more sort of in the brain, in the motor center of the brain that does voluntary actions. But you got spinal level reflex controllers, but they add up. They produce the signals that come out of each of them add together to produce the final signal to send to each of the muscles. So these are vectors over here. A is the vector of signals that get sent to the on the output over here, the vector of signals that get sent to the muscles in each neuromuscular controller. So for each complex, I mean, so for the torso complex, you have a vector of 400 plus signals that get sent to each of the muscles in that complex, and so on. And so each of these is a deep neural network, and this is a recurrent structure because the deep neural network send changes in the activation. They're trained to produce changes, but they take in the current activation vector plus something to do here, which is the discrepancy, let's call it. You'll get an idea later of how this works. And then they produce changes to the activation, which then get added to the current activation to produce the activation in the next step, so to speak. So this is a recurrent neural network, or controller, I should say. But each of these are feed-forward deep neural networks, or DNNs. So what do they look like? Well, okay, here's the DNN architecture for the cervical cephalic, the head-neck voluntary controller. So here, two thetas are the desired change in orientation of the head, theta and phi. Well, there's also another degree of freedom as well, but just to simplify matters, it's just theta and phi, theta horizontally, phi vertically. So that's the pose of the head. And here are the activations of all the muscles that are the current activation of the state of the head neck system. And then the neural network gets trained to produce the change in activation. And so what this is incrementally trying to do is, if I want to change my pose, then what I want to do is change my activation from the current one so that I can get, closer and closer to the desired changed pose. So hopefully these changes are not too large, that the network can actually learn to move naturally, to kind of zoom in and make this difference as small as possible, down to zero, which means you've achieved your goal. So you can see that these networks are, first of all, they're fully connected networks. And each of these 6 hidden layers, 300 hidden units in each layer. And this worked for us. I mean, we were able, and we tried to keep the architecture as uniform as possible. So here's for a limb, an arm or a leg. You got the end effector position, delta X, delta Y, delta Z, and then, you got the change in activation that's required. And here's the reflex controller architecture for these controllers. Again, 6 hidden layers, 300 units in each layer. And here we see strain rate, so strains of the muscles and strain rates. I don't want to get into the details of this because it's a little bit involved. So anyway, that's the reflex level. So just to show you then, for the core neuromuscular controller, we've got, this one's a bigger one. So we have to use 600 hidden units in these networks. So again, the voluntary and the reflex on this side. And you could see how many weights there are. There's like 5 million weights in this, and 900, almost 10,000 ReLU units in this controller, which is the biggest one. So just to show you how this works then, let's say we turn off the controllers. Okay, the head and the arm just kind of flop down uncontrolled, but when we turn them back on, they sort of come back. Now, how do we train this system? Let's look at the arm, for example. Let's suppose we want to reach a target, which is this white sphere over here. Well, from this position, there's an error vector or discrepancy from where we are to where we want to go. Well, okay, we can kind of solve by inverse kinematics how to take an incremental step in the right direction over here, and by inverse dynamics, how to change the activation of the muscles in order to make this step against gravity, just like I explained before with the neck. And then we can do muscle optimization. So we want to make this step while using the least amount of muscle effort, and then we have it. So we can actually take an incremental step in the right direction with our arm. And this is a loop that produces training data on the fly to do this by solving incrementally inverse kinematics and and inverse dynamics and muscle optimization problems, which are computationally expensive. But again, remember, this is just for synthesizing training data. It's all done offline. Once the data is synthesized, the model then learns from this training data. So now you can see the learning process. At the beginning, the model is totally out of control. The arms and the legs are just flying around, wildly out of control, can't do the right thing. But as we give it more and more training data and more epochs in the training process, the model, the arm can then, it learns how to control its arm. At first, it's kind of jittery, but later the jitters go away and it becomes, fairly smooth and is able to raise the arm in gravity against gravity and reach out and touch the target. And here you could see fully trained. If it's properly trained and fully trained, then it can do a smooth motion and reach for the target. Here's another more complicated case, which is, whoops, I'm sorry. This is sorry. Let me try this again. A sit to stand. So it's sitting in a sitting pose and it wants to stand up. And at first it just falls over, but as the training progresses, it's able to do a proper sit to stand action. Other things it can do is balance and gravity. Remember, this is a physics model, so it's got mass. The mass of the torso and everything are modeled. So this is causing big swings in the center of gravity, doing these kind of torso calisthenic exercises. And so it has to maintain, our virtual human maintains balance in gravity on its two legs as it's doing this. Now, finally, let me. So we have a model that can actually balance itself. It could stand upright. You'll see later it could take steps. Now we have to say, well, let's look at the problem of sensory motor control, where we model, for example, vision as a start. Let's model visual perception and, from the eye to the brain, and then build that into the loop as well, so we can have a fully integrated sensory motor system that we can get our virtual human to do things like real people do. Now, if you look at vision, it's complicated and difficult. I mean, here you see the visual pathway in more detail. It's not just straightforward like this, but I mean, the cortex in the back, the visual cortex in the back of the brain, the eyes are connected through this optic channel over here, and they cross over and so on and so forth. And much of this is still mysterious, but neuroscientists are making progress on understanding this, and perception scientists as well, and so on. So we know some of it, but anyway, we're trying to model this to some level of detail which is reasonable. Not try to get ourselves kind of hung up on too much detail where we'll just not be able to solve the bigger problem. Anyway, one of the important details that we have to do is modeling the eye itself. I think this is very, very important, the eye and the retina. And as you probably already know, the eye itself is a very complicated organ. The retina is complicated as well. And the eye is not a camera in the sense of a cell phone camera or a CCD camera on a camera. The eye has photoreceptors. The retina has photoreceptors in the back over here. So here's the optic nerve where the blind spot. This is the fovea over here, this embedded area with lots of photoreceptors. If you look at the distribution of photoreceptors, you see that, okay, first of all, there are rods and cones. Rods are for night vision, just black and white, monochrome night vision, and cones are for color vision during the day where there's lots of light. We're trying to model the cones in what I'm showing you. So we have Rgb color vision. The optic, so this is showing density of photoreceptors relative to eccentricity away from the fovea. So 0 degrees is the fovea. And then as you go this way or that way along the retina, you have higher and higher eccentricity in terms of degrees. And you could see here that the, let's see, the cones are dotted. So cones have high density at the fovea and quickly drops off in the peripheral vision. And the rods have 0 density in the fovea, but it increases rapidly and then decreases from there. And this is the blind spot over here where there are no rods or cones, which is right over here where the optic nerve comes through. Okay, so optic nerve and also vessels that supply blood to the eye. And over here you could see kind of cones and rods. So the retina is kind of reversed. Here's sort of the inside of the eye, and the rods and the cones are sort of to the back over here, back behind. But this is all kind of transparent anyway. Anyhow, and here's what it looks like. You know, if you're looking at an electron microscope at the retina, you could see kind of eccentricity away from the center. So here you have high density, and it gets to lower and lower density coming out of here. Okay, so it's complicated. But here's our model of the eye. We see we have the geometry of the eye over here, the different sub-organs of the eye, including the lens and so on, and the iris. And here's the retina in the back. And each point over here is a photoreceptor, a cone photoreceptor. And this distribution is what is known as a noisy log polar distribution. It's kind of modeled in the same, you can see high density photoreceptors at the fovea and lower density towards the periphery of the retina. Here's what it looks like mathematically, noisy log polar. And here you could see flattened out, you could see high density of photoreceptors and lower density for a certain number of photoreceptors, 3,600 over here. So what comes out of here is not an image, but it's just a vector. Each component of the vector is just simply the response of each photoreceptor to the light hitting the retina. So just it's a one-dimensional vector, a photoresponse of photoreceptor responses. We call that the optic nerve vector, or ONV. Now, the other thing that we need to do is model eye movements. So the eye has muscles. There are 6 extraocular eye muscles. You can see them here, and here are their names. And these are the muscles that make eye movements. Because we don't have uniform vision, we only have high acuity vision at the fovea, which is about 2 thumbs at arm's length. That's sort of the degrees at which we can read writing. But away from that, we can see a broad field of view, but much lower resolution. So we're aware of what's around us, like 180 degrees out from the eyes. But in order to read and look at things very accurately, we have to move the muscle of the muscles of the eyes have to contract. The eyeball rotates and looks at something of interest. So that's attention. Anyhow, here we can see a simulation of this, showing how the muscles of the eye over here, this is a disembodied eyeball, and it rotates, and the iris works also with the light. So the way we compute how much light hits the photoreceptors is through ray tracing, which is a computer graphics rendering technique, but it's basically ray optics. And so if you want to know how much light is hitting from your virtual environment, a particular point on the back of the eye, the retina, at that location, it's very easy to do. You shoot a ray out from that point, it gets diffracted, diffracted through the lens, goes out the pupil. In fact, you have to shoot multiple rays from that location to sample the pupil area because this is a finite aperture, and you send it out and the rays bounce in the environment, collecting light, and it's a recursive process. When it comes back, it tells you how much light hits you right at that photoreceptor. And that's what the photoreceptor response is then, that gets sent through the optic nerve vector to the brain to then do analysis to figure out what we're looking at. So that's how it works here. And you can see here the ocular motor control system. We've got a deep neural network over here that controls the muscles of the eye, another deep neural network that interprets what gets seen, and then shallow neural networks, 2 of them, that show you, that control the iris and the lens. And again, the neural networks look similar to the ones before. Here's the shallow neural network, because the sphincter muscles for the iris and the lens are just 1 degree of freedom muscles. You know, it's just like a sphincter, and activating it just kind of dilates the pupil or contracts the pupil or pulls on the lens, and the lens goes from being round like this to being like that. And that, as you'll see in a moment, focuses right here. Okay, so that kind of illustrates. But if we have many photoreceptors, we can't use a fully connected network. We can't use a convolutional neural network either, because these are not, as I said, this is not a camera. We don't have an array of pixels like we have in a camera of equal resolution across the entire image, just a regular array of pixels, rectangular array of pixels. We have this non-uniform distribution, so we have to create receptive fields that we call this. Sorry, this is showing. So this is what we call this. We call this in irregular, locally connected irregular network, or LINET, or LINET. And the idea is each neuron has a receptive field over here, which and so roughly the same number of photoreceptors in the receptive field. So the receptor fields in the middle here at the fovea, which are very dense, are going to be small, and they naturally get larger as you get to the periphery. And this models kind of what's known about how photoreceptive fields work in human vision with the human retina. Anyway, I can't get into the details of that, but here you can kind of see in this simulation, you could see that there's a visual target, which is a white sphere, and here he's sitting down and he can put out his arms and reach the target. And this one showed all the rays that are coming out, or some of the rays that are coming out, but these, this is just part of the computation that you don't see normally, you shouldn't see. And so here's how it looks on the retina, where the white sphere, the eyes are rotating so that the white sphere, which starts off at the periphery on the outside, with the eye rotation, the white sphere comes to the center, where all the high density of photoreceptors are. So the eye rotation happens, and then you look at your visual target. And here's how it looks, where the visual target comes out, gets shot from this cannon, and he is now able to reach out and intercept the visual target, which is sensory motor control. And this is happening online, and he's learned how to do this and can then do it online on the fly without very efficiently. Here's, well, if you do a full rendering, you know, with all the fancy computer graphics, kind of this is more like what it looks like. Anyway, just in the interest of time, let me proceed with another example here, a little bit more difficult in terms of hitting your target where it's bouncing around. Oops, this should have played multiple times. Can I do it again? There. You could see it's all natural, basically, in the sense that the head moves, the neck controls the head, the eyes are moving within their sockets properly, and then the arm reaches out and can intercept the visual target. And so here in this diagram is the complete visual motor control system with all the neural networks that are involved here. The upper part is the vision subsystem. The lower part is the motor subsystem. Here we have the two eyes, the right eye on this side, left eye on this side, and their own. This is the oculomotor control system for each eye over here. And then we talked about the motor control system with its the body motor control system with its 6 neuromuscular motor controllers. And then I can't go into the details of this part too much, but basically what we have here are an additional, what is this, 12 or so, I guess, 10 deep neural networks up here that are analyzing the visual information that's coming from the optic nerve vector from the retinas down to, to the visual cortex in the artificial brain over here. Yeah, so it's a total of 24 deep neural networks and 4 shallow neural networks. And you can see here the 4 shallow neural networks are for the eyes, and then the deep neural networks are for the vision system and sort of the eyes. There's a deep neural network over here sorry, these are deep neural networks for the eye muscle. So they're down here. 14 deep neural networks for muscle control in our model, plus 10 for vision. So this is a big, kind of a monster deep learning system here that has been trained to control our model. So some of the things it can do is golf strokes. Here it's he's balancing in gravity on 2 legs and is making controlled strokes with the club, with the putting to do a sink a putt. And he just goes harder and harder until he finally sinks it. Here you see he can step up to the putt and get into position and nail it. Okay, so this is sensory motor control with balance and all of that. Here's another example showing a goaltender. So that's that demonstration. And I have one final demonstration for you, which involves higher level vision, at least some amount of higher level vision. What we were trying to do here is tackle the kind of complex problem of, can we look at a sketch? So here you see some sketches down here. These are like hand sketches that people can, doodles or something like that people can draw. And can we make our virtual human draw one of these doodles by just looking at it, interpreting what it's seen, and produce arm movements with a finger? You're going to see it here on a touch screen display where you can actually reproduce this sketch on his own. So what we did for this was use what's known as sketch RNN. This is sort of a Google system that has been trained. It's been trained on lots of examples of sketches like this, hand-drawn sketches where people the pen trajectory, recording of pen strokes has been recorded for each of these sketches. So what you have is an image. You have a regular pixel image of the sketch over here, plus the pen strokes that were done to create that sketch. Okay, and you have lots of examples of this from many people doing this. And so Google, is able to train a deep neural network with an encoder-decoder structure like this that can do this sort of thing. So we had to modify this because we have a retina. But with the same approach basically. So they showed it could work. So then, if you show it a sketch, it basically can produce the pen strokes that were required. And for other sketches that are sort of never seen before. So somebody comes in and draws something new, then the system can actually give you the sequence of pen strokes that can produce a reasonable copy of that sketch just from an image of it. That's what the trained system can do. So we modified this, but it's essentially the same idea, modified it so that it works with the ONV, the optic nerve vector that comes out of the retina of our eye model for a virtual human. So here you can see some of the retinal images. Well, you can see kind of the photoreceptor patterns that get stimulated by that sort of thing from each of these sketches. So this is well, what the retinal image looks like. So it's kind of different from the regular image of the sketch. Anyway, with this modified version, okay, so this is the data set is called Quick Draw, and here's the data. And so that's the same data set that we used, and we trained our own system with just taking retinal images by having the eye look at a sketch like this and create a retinal image, and then training from these retinal images. So it's a modified version of what Google has. And so here, what we have is our virtual human. Okay. So this is done completely automatically. So completely autonomously, and he's balancing. So he can step up to the display, balance, use his arms and neck and eyes are, looking at paying attention to what needs to be paid attention to, and the whole thing works completely autonomously. And steps back, and it's done. So that is the end, basically, of what I wanted to show you today. And let me finish here by acknowledging the students that have been involved here in this work, both PhD students, of course, but also a master's student and even a bachelor student, as well as a postdoc, that have been involved in various aspects of this big project over the years. And in fact, this is a sequence of PhD theses, starting with Sung-Hee Lee, who's now a professor at KAIST in Korea, his home country. And he built the biomechanical model in the first place before we had really he did the neck modeling that I showed you early on, and then built the full body model as part of his PhD thesis, but we didn't have the ability to control it then. And then Justin C., who's currently at Facebook, is did for his PhD the swimmer for his PhD with the CP gene control. Then Masaki Nakata did the important task of the neuromuscular control and sensory motor control of the full body model. And in conjunction with Tao Zhou over here, they did the neuromuscular torso control. And finally, our model could actually stand up, balance, and do those last demos that I showed you of the golfing and the sketching and all of that. And then also Arjun Laxmipathy, who's now a PhD student at CMU, did the biomechanical eye model and a ocular motor control of the eye, and Honglin Chen the line nets, and Eftikios Sefakis, who did the soft body simulation much earlier on. And even though I think this is important work, to be honest, I haven't been able to get much funding for doing this kind of work from regular channels, meaning National Science Foundation or whatever. I had an early grant from DARPA, that kind of a small grant that actually started a somewhat earlier project than this. But ever since then, it's been basically funding from UCLA, the Guggenheim Foundation, NYU, because Sung-Hee Lee started his work at NYU with me. And most of the funding for doing this is actually coming from Voxel Cloud, which actually supports the students. This is my startup company, which is not involved in this work, but it's deep learning for medical image analysis is what Voxel Cloud is all about. But, I can kind of give funding to myself from Voxel Cloud, where I can use that to support for student support, and then, have them do wonderful work like this. So I'm very proud of all my students, and, they do all the hard work of making all of this stuff work. And for me, it's sort of the big ideas, let's say. But anyway, they do a lot of solve all the problems along the way. So thank you very much for having me here today. And if there are any questions, I'd be happy to answer them if there's time. Otherwise, thanks again. And you can look on my website if you like to get papers, videos, demos, that kind of thing. Thank you.
Yeah, just a few catch-up questions. That is like, what kind of like tools? I found that you are trying to use like the deep learning stuff that is for simulation, right? For like doing the research projects, for like simulating the human muscle. What kind of tools that you may talk of, like?
Well, I just want to say that we're not using deep learning to simulate the muscle. We're using deep learning to control the muscle, right? Yeah. So the simulation of the muscle in these works is done by numerical simulation, and it's accurate. It's physically accurate. But the neural network of the brain is what's controlling the muscle, and that's what's using deep learning trained on simulated data that gets synthesized. Because in the real world, our bodies synthesize training data by the physics of the universe, making things do things, So that, if you understand what I'm saying. Mm. Yeah. But there are lots of different pieces of code here. There's 3 different types of simulators. There's all the neural network code and all, the TensorFlow, and, we use all those libraries for the deep neural network. So, we're not, except for the line nets, we're not really trying to advance machine learning per se. This is sort of you can think of it as an application of machine learning, but we're kind of using the latest machine learning stuff that we can, because this is a challenging problem, both on the perceptual side, the vision side, and on the motor control side as well. So we use,
Just for...
Oops. Let me see, maybe my...
What would you suggest for like the research direction in the future for like doing research?
Well, there's so many open problems here. I mean, what we're doing, although I think we've made major strides, in solving some, in looking, in addressing some deep problems. Still, this is just scratching the surface of what the human brain can do. And, there's so many open problems in between every problem. I mean, for me, it's sort of like, you look at between any two kind of solutions, and there's an infinite number of problems to be solved in between. So it's sort of like the real number line, where between any two numbers there are an infinite number of other numbers. And I mean, this will keep going indefinitely, perhaps. But so one of the things we want to try to do is online learning, where incorporating some reinforcement learning that we've done for simpler cases in the past with virtual animals. Try to do reinforcement learning in sort of this context, but it has to be done at a higher level. I think what we've done here with deep learning, without sort of reinforcement on the fly, is sort of the low-level learning process. And then we have to put on top of that reinforcement learning for sort of higher level sensory motor control. So that's a big issue right there that we want to try to solve. And as I said, every day we're trying to close the gap between virtual reality and physical reality. And we're hoping that in the future that there will be no gap. Basically, you won't be able to tell the difference between a virtual human in its virtual world and a real human in its real world. They'll behave the same, and you can immerse yourself into this virtual world, and you'll think you're in the Matrix or something, right? No difference from the real world. Or you can of course change virtual reality so it behaves differently from physical reality if you like. But yeah, that's in a nutshell what the philosophy here is.
Okay, so thank you very much for your insightful talk. And then so thank you very much for Dimitri's very insightful talk. So
Okay.
If there is like I think there is a comment. I think we need to, in research, to focus on another type of the actuator instead of like normal motor.
Yeah, I mean, there's lots we can do to improve these different actuators. Yeah, I think probably you're referring to robotic actuators, right? When you say that, there are artificial muscles that are trying to kind of be contractile and so on, more like the real muscle. Thank you very much for your kind comments here. I truly appreciate it. Yeah, so many. Let's see. What other? Are there any? I don't want to run too much overtime because there are other speakers.
Yeah. We will have got another speaker in the afternoon section, so we can continue with the discussion in the afternoon. So thank you very much for Dimitri's excellent talk. Okay, we actually benefit a lot. Thank you very much.
My pleasure. My
Yeah,
pleasure.
Thank you.
Thank you.
Thank you, Dimitri. Thank you very much. Thank you.
So we will
You're welcome, Gabriel. Thank you. Thank you for inviting me, the both of you. Thank you.
Yeah.
Thank you.
So we will just we will in touch. We'll be in touch again with you, and then so thank you very much for everybody. So we will just end up here. So see you in the afternoon section for all of you. Thank you. Bye bye.
Thank you.
Bye bye.
Bye. Keep in touch. Happy New Year.
Thank you.
Yeah, Happy New Year.
Too.
Yeah. Happy New Year.
Yeah, Happy New Year. Bye.
Bye.
Bye for now. Bye.
Yeah. See you in the afternoon, Gabriel.
See you.
Well, you haven't